Our discussion here today will be about the nature of light. And that's a broad subject. We're not going to get into all the quantum physics and everything else that are behind it. In fact, that's how quantum physics came about, was by studying light. We're not going to go that far, but we will get into a little bit of understanding of the atomic structure of things, because that's how light is really produced. Whether we're looking at a candle, a bonfire, something that's producing light by heat and by flame, an incandescent lamp or an HID lamp that uses gaseous discharges and ionization to produce light, or today's current technology with LEDs, or whatever comes down in the future as far as a source is concerned, light is always produced at the same way. Light is light on an atomic level. Now, the nature of light is that it's an electromagnetic radiation, and it displays both the characteristics of wave and particle. That's where we get into the quantum physics. Don't worry about it. We'll make this simple for you as we go on the discussion. When we look at the electromagnetic band, or frequencies out there that fall in the electromagnetic spectrum, we find that light, the visible portion of the spectrum that we see as light, is very, very narrow by comparison. On the extreme low end, we're talking about radio waves, AM and FM. We get into microwaves at that point as well. Above that, we have X-rays or gamma waves. Just to give a little example of technology shifts over time, at one time, down in that extremely low end of the spectrum is where your remote controls for televisions used to work. And so you could change your channels in one room on a television and have a television in another room changing channels, or if you were in an apartment building, you could change your neighbor's stations with your remote control because it could pass through the walls. So what's happened over time is now most remote control devices use infrared LEDs that operate in that infrared spectrum, that IR spectrum that you see here, and that's how we limit the flow of the signal, so it doesn't go into an adjoining room and then change stations on someone else's set, or change volume levels on someone else's radio or television. But this visible spectrum ranging from red to blue, when we talk about increasing the wavelength, that means that the wavelength gets longer, or it goes more towards the red side in the visible spectrum. When we talk about increasing the frequency, the wavelength gets shorter and it goes towards the blue side. Just to make sure we've got the understanding there of both of those terms. Interestingly enough, in the electromagnetic spectrum, all frequencies travel at the same speed. Now, that's really important in color, because can you imagine, since white light is made up of all the different colors of the visible spectrum, if red and blue light traveled at different rates, what things would look like if this was the case? That would really be odd. Now, we do get a certain kind of impact called a Doppler shift by an object moving away from the Earth or towards the Earth, much the same as in sound waves. When you have a siren from an emergency vehicle moving towards you or away from you, there is a little bit of shift in the sound of it, because it moves more towards the low end or more towards the high end. But it's across the board in everything that's contained in that bundle of frequencies that occurs. It's called a Doppler effect. Now, again, as light has both the characteristics of wave and particle, measuring it and understanding what it does comes in two different forms. If we treat it as a waveform, much the same as you would use with a tuning fork, amplitude then changes the volume. So we can take a sound signal, we strike, that you see on the top level here, we strike a tuning fork. The tuning fork vibrates at a particular frequency, and you'll notice from the first slide on the left to the middle slide, the frequency doesn't change. The timing from the peaks to the peaks don't change. However, the amplitude does change, and that's the volume decreasing until you reach a flat line. When we're talking about an optical signal, going from an optical signal to a blank screen, it's not the same thing. What we're going about on the optical side is we're going from a bundle of particles and frequencies to fewer particles or frequencies, or fewer and fewer and fewer, until there's nothing, and then that represents a zero or flat line. It's not an amplitude issue, it's more of a volume issue there in the amount of information contained within the packet of the particle. So sound waves also need solids to travel: air, water, gas. sound does not travel in a vacuum. But when you move into outer space and you get into the space program, for example, both light can travel through space, thus we can see stars, and radio waves can travel through space, thus there's communication between the shuttle and ground-based radio stations here on Earth, because those elements, those frequencies in that electromagnetic spectrum can travel in a vacuum. And that's another thing that helps to appreciate that it's not just a waveform, but also functions as a particle. In determining the particle nature of light, there were experiments that were done in the late 19th and early 20th century in order to get a better understanding of this. One of the processes that was done, experiments that was done, was to take a source of light and pass it through a filter in order to narrow down the frequency of light, or color is what we think of. Frequency of light and color are essentially the same thing. And then focus it onto a metal surface. By doing that, the light frequency or color is shined on a particular kind of metal, and the two of them working in conjunction with each other would then allow or produce electrons to flow. And as long as they're bled off of that piece of metal, or as long as they're emitted from that metal, this process would then continue and have an electrical flow. Now, the production of electron flow or emission isn't dependent upon the intensity of the light. So we don't take, for example, it's blue lines that are used here. So let's say blue light was used. We don't take the blue light and intensify the blue light in order to get more electron flow, but it's the color or the frequency of the light that becomes important. Until that proper frequency or color is reached, no electrons are freed from the metal. And this color or frequency is referred to as a threshold frequency. That's the technical term for it. Above it, electrons that have absorbed energy in the form of photon packets may be conducted away as electricity, and below it, nothing happens, no matter how much the intensity. This process is called the photoelectric effect, and it's basically the concept behind photovoltaic cells. Again, here we're talking about kind of a reverse situation of producing light, but understanding how it works helps us to understand how light is produced. Let's take the element potassium. If we take potassium and strike it with light, and we use a waveform of light that is below 540 nanometers, nothing happens. But when we go above 540 nanometers, it's about a visible green light, then we start to produce electron flow, or electrons are emitted from the potassium. The higher the frequency, the more electrons are emitted from it. And so we begin to get electron flow because the electrons are absorbing that light as energy and causing them to be activated. Kind of an interesting process, no? There's a device to be able to understand how this works, and it's called an electroscope. An electroscope is a device that measures radiated electrical charges, a static electricity, for example. The diagram here is of a very basic, what's called a gold leaf electroscope. Now, in this gold leaf electroscope, the metal box, the container that you see here, would be made out of metal, and a vacuum would be created on the inside. There's a metal cap with a stem on it that are the same material that extend down into the box, and attached to it, not electrically or conductively, but just attached to it is a gold leaf that when you have this all put together and give it a few moments, what happens, the gold leaf begins to bend away from the stem, because the gold leaf has the same negative potential as the stem does. And since we know in magnetism that like poles repel, the electrons in the gold leaf and the electrons in the metal stem cause the two to bend away from each other. That's the reason why you see that gold leaf then bending away. But if what we do now is to shine light above the threshold frequency of the cap material on that cap, then the electroscope starts to discharge electrons, and the gold leaf falls limp to the side of the stem. And that's another way of identifying the fact that there is electron flow going on in this process. Now, how is light produced, though? What's the process? And it's kind of the reverse of this. Let's take a look at the example or the illustration of the atom that you see here on the right. Now, this atom, in its outermost band, its sixth band, can have a maximum of 72 electrons, and in the next to the outer band would be 50. Atoms have a limited number of what they call shells or orbits around them, or electrons that can inhabit those orbits or those shells. Once you reach that level, they have to go to the next level out, and that's part of what identifies a particular element, is what its atomic structure looks like. And here what we see is, even though there can be a lot more electrons stored in this atom, they're not there. That's the nature of this particular material. Now, we can energize these electrons through the application of heat or through electrical bias. And if we do that, what occurs is the energized electrons now move to higher orbits with this stored energy, because now what they want to do is break free and get away from the atom itself. When we get it up high enough, that's when the electrons begin to flow to neighboring atoms, and we have conductivity take place. That's electrical flow that takes place. That can happen either through the application of electricity or through the application of heat. Now, in this particular instance, what then happens is, when they ultimately move to neighboring atoms, their nature drives them to settle into lower orbits, and in doing so, they release that stored up energy in the form of a photon. Now, this particular atom that we're seeing here is a tungsten atom. The room for movement of electrons is one of the features that makes tungsten an ideal choice as material for incandescent lamp filaments. The fact that you have so much room for electrons to move into the 5th and the 6th orbital band, because there's so few that are there, and the fact that tungsten has an extremely high melting temperature. That's the reason it was used as the choice of material for incandescent lamp filaments. Now, the process of incandescence in producing light is the process of heating up the atomic structure. So if we take electricity and use that to generate heat, we've got a step there in the transference of processes that generates losses. And this is one of the reasons why incandescent lamps are among the least efficient forms of producing light. Now, you can get even less efficient than that if you just use heat, for instance, in heating up a horseshoe or a piece of metal until it starts to glow. That's an extremely inefficient way of producing heat. But that's the process or the nature of light, and it doesn't matter what the material is or what the light is that you're looking at. The production of light on the atomic level is always the same.